Have you ever wondered how a site like Amazon or Google can find that one thing you're looking for out of billions of items in like a split second? Well, the secret isn't just about having super fast computers. A lot of the time, it's about using a beautifully simple, incredibly powerful algorithm, one you probably use every day and don't even realize it. Today, we're pulling back the curtain on the magic of binary search.
So here's what we're going to do. We'll kick things off with a really basic problem. Then we'll look at the elegant trick that solves it, and we'll see why that solution is just mind-blowingly fast. After that, we'll see how this one simple idea is used to power everything from fundamental code structures to the gigantic databases that basically run the modern world. Let's dive in.
All right, let's start with the fundamental challenge. A huge part of what computers do is just finding one specific piece of information in a giant sea of data. But what if that data is sorted? Well, then it's less like finding a needle in a haystack and more like finding a specific word in a dictionary. The order is everything.
To make this super clear, let's use a classic example. Imagine I gave you a huge old-school phone book, like a million names in it, all sorted alphabetically, and I told you to find John Smith. How would you do it? I mean, there's no way you'd start at the very first page with the letter A and then just flip every single page one by one, right? Your brain is way more efficient than that.
You know, intuitively, what to do. You'd crack the book open right to the middle. You'd land somewhere in the M's, and instantly you'd know Smith has to be in the second half. Just like that, you've thrown away 500,000 names without even thinking about it. You do it again and again, splitting the problem in half each time. Well, that little intuitive trick you just used, that's it. That's the heart and soul of binary search.
So this jump to the middle trick is the key. It's a perfect showcase of a really powerful problem-solving strategy called divide and conquer. You take a massive problem, you chop it into smaller pieces, and you just keep chopping until the pieces are so small they're trivial to solve.
Okay, so here's the formal textbook definition. But really, there's just one rule you absolutely have to remember for this to work. The list must be sorted. If it's sorted, you can play this divide and conquer game and toss out half the data with every single guess. That's the whole secret.
All right, let's see this in action. Forget the phone book for a second. Here's a simple, sorted list of 9 numbers. Think of it as our little playground. We've got a low end at index 1 and a high end at index 9.
Our target, the number we're trying to find, is 82. So right now, our search area is the entire list, from start to finish. Let's begin the hunt.
Just watch how fast we can pinpoint our number. First step, we jump right to the middle, which is index 5. The number there is 9. Okay, is our number 82 bigger or smaller than 9? It's bigger, right? So we know it can't be anywhere in that first half. Poof! We just eliminated half the list. Our search is now just from index 6 to 9. Let's do it again. The new middle is index 7, where the value is 54. Again, 82 is bigger, so we throw away that new left half. All that's left is index 8 and 9. We check the middle, index 8, and bam, there it is. The value is 82. We found it. It only took us 3 checks to search the whole thing.
And this is basically what that logic looks like as code. Now don't worry about the specific syntax here. Just look at the pattern. You've got a loop that keeps going as long as there's still a search area. Inside it finds the middle, does a quick comparison, and here's the key part, it moves either the low or high marker. It's literally just our phone book strategy written down for a computer to follow.
So, we've seen how it works. But now for the really amazing part. Why is this algorithm considered so powerful? Why is it so unbelievably fast? This is where things get really cool.
The dumb, brute force way to do this is what's called a linear search. That's our flip every page method. And sure, it'll get the job done, eventually. But binary search is playing a completely different sport. It's just so much faster because it's not getting rid of one item at a time, it's getting rid of half of the remaining problem with every single step.
Okay, let's go back to our phone book with 1 million names. If you use the linear search, in the worst case, you might have to make 1 million comparisons. 1 million! But with binary search, you can find any name in that entire book in, at most, about 20 comparisons. Just let that sink in for a second. We went from 1 million steps down to 20. That is the insane power of what computer scientists call logarithmic time, or O of log n. It means that even as your list gets gigantic, the number of steps it takes to search it barely even grows.
And this is the most important part. A legendary computer science textbook says that these kinds of algorithmic differences are often much more significant than differences due to hardware and software. What that really means is, choosing a smart algorithm is way more important than just having a faster computer. A clever strategy will always beat brute force.
Okay, so this algorithm is a beast for static, sorted lists. But what happens when your data is messy and always changing? Well, this leads us to the first big way this divide and conquer idea gets used in the real world, the binary search tree.
Think about it. A sorted list is great, but it's got a huge flaw. If you want to add a new number, you have to find the right spot and then shift everything else down to make room. That's super slow. So what do you do when your data is alive, when things are being added and deleted all the time?
This is the exact problem that binary search trees were invented to solve. They take that core logic of binary search, that is my target smaller or larger question, and build it into a physical tree structure. From any given spot or node, everything smaller goes to the left and everything bigger goes to the right. This one simple rule means you can search, add, and delete items, all incredibly fast, usually with that same amazing O of log n speed.
Now let's take this one step further. What happens when your data is so ridiculously big it can't even fit in your computer's memory? Now we're talking about the huge databases that power social media, your bank, online shopping, everything.
See, when your data lives on a physical hard drive, your computer speed isn't the problem anymore. The real bottleneck is the physical time it takes for a little mechanical arm to move and find the data on a spinning platter. It is thousands upon thousands of times slower than just looking at something in memory. A regular binary search would be painfully slow here.
And this is where something called a B-tree comes to the rescue. You can think of it as a binary search that's been beefed up for hard drives. Instead of a simple two-way left or right decision, a B-tree can hold lots of values in one spot and branch out in many different directions. It's designed so that each big chunk of data fits perfectly into what a disk reads at one time. The end result? It dramatically cuts down on those slow disk reads and lets us search through massive databases with incredible speed.
So we went from a simple phone book all the way up to the massive engines that run our digital lives. What's the big lesson in all of this? What's the main takeaway?
I think this quote from that same textbook just nails it. Understanding concepts like binary search isn't just about passing a test. This is what separates people who can just write code from people who can build truly efficient, amazing systems. It's the difference between writing code that just works and writing code that works brilliantly.
At the end of the day, binary search teaches us something way bigger than just how to find a number. It teaches us a powerful way of thinking. This divide and conquer strategy, taking a huge, scary problem and just chopping it in half, again and again until it's simple, is one of the most powerful tools you can have in your mental toolkit. And once you start looking for it, you see this strategy everywhere, from fixing a bug in your code to planning a massive project. So the question I want to leave you with is this. What's a big, complex problem in your world that you could start solving by simply and repeatedly cutting it in half?